Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A certain intellectual gravity pervades the world of mathematics in the early 20th century. It pulls the most ambitious minds toward the high peaks of abstraction, a landscape recently and spectacularly reshaped by the school of Emmy Noether in Göttingen. Here, the raw material of mathematics was being forged into elegant axiomatic systems. The theories of groups, rings and fields stood as monumental achievements, each a self-contained universe governed by a sparse and powerful set of rules. This was a world of pure structure, where the properties of algebraic objects could be deduced with crystalline clarity from first principles. The power of this approach was immense, offering a new and profound unity to disparate areas of number theory, geometry, and analysis. Yet, alongside these well-defined domains, another fundamental concept remained a ghost in the machine. The idea of order, the very notion of one thing being before another, smaller than another, or a component of another, was ubiquitous. It appeared in the logic of propositions, where one statement implies another. It was present in set theory, where one set is a subset of another. It was fundamental to number theory, where one integer divides another. These were relationships of hierarchy and dependence, essential to mathematical reasoning. They were, however, tools used in parsing, concepts employed for specific arguments within other, more formalized theories. The idea of an abstract theory of order itself, a discipline that would treat the relation less than or equal to with the same structural seriousness as the operation plus, remained a scattered and unrealized possibility. Into this environment steps a young Garrett Birkhoff, a mathematician whose legacy would become one of synthesis and bridge building. As the son of the distinguished Harvard mathematician George David Birkhoff, he was born into the American mathematical aristocracy. He possessed an inherited familiarity with the grand problems of analysis and dynamics, yet his own intellectual trajectory would carve a distinct and perhaps even more foundational path. He saw in the scattered uses of order relations a deep, underlying unity, waiting for its own language, its own axioms, its own champion. The initial step in this codification was the formal definition of a partially ordered set, or what we now call a poset. The idea is deceptively simple and profoundly general. A poset consists of a collection of elements along with a relation, let us say precedes, that satisfies three elementary properties. First, every element precedes itself, a property called reflexivity. Second, if element A precedes element B and B precedes A, then A and B must be the same element, a condition of antisymmetry. Third, if A precedes B and B precedes C, then A must precede C, the familiar property of transitivity. This abstract definition captures a startling variety of phenomena. The set of all subsets of a given collection, ordered by the relation, is a subset of, forms a poset. The natural numbers, ordered by the relation divides, form another. The very structure of family lineage, ordered by an ancestor, forms a poset. The key insight is that the order may be partial. Some pairs of elements may be incomparable. For instance, in the set of numbers from 1 to 10, 3 divides 6, but 3 has no divisibility relationship with 5. They are simply different branches in the hierarchy. This concept of a partially ordered set provided the general landscape. From this vast territory, Birkhoff, in parallel with the brilliant Norwegian mathematician Øystein Ore, began to map a particularly rich and structured region, the lattice. A lattice is a special kind of partially ordered set where any two elements have a unique greatest lower bound and a unique least upper bound. The greatest lower bound of two elements, A and B, is an element that precedes both A and B, and is preceded by any other element that also precedes them both. This is often called the meets of A and B. Symmetrically, the least upper bound is an element that is preceded by both A and B, and which precedes any other element with this property. This is the join. These abstract definitions spring to life with familiar examples. Consider again the posit of all subsets of a set, ordered by inclusion. The meet of two subsets is their intersection. It is the largest set contained within both. The join is their union. It is the smallest set that contains both. For the integers ordered by divisibility, the meet of two numbers is their greatest common divisor, while their join is their least common multiple. Suddenly, concepts from elementary number theory and set theory were revealed as two different manifestations of the same underlying algebraic structure. The operations of meets and join gave the amorphous notion of a posit, a concrete computational character akin to the addition and multiplication of a ring. This work culminated in his 1940 monograph, simply titled Lattice Theory. This book was an act of intellectual consolidation on a grand scale. It gathered the nascent results, the scattered examples, and the foundational definitions into a single, comprehensive and formidable volume. It established lattice theory as a distinct and vital branch of modern algebra. The book provided the field with its foundational vocabulary, its central theorems, and a host of open problems that would drive research for decades. It became the canonical reference, the text from which generations of mathematicians would learn the subject, establishing Birkhoff as the principal architect of this new domain. Within this text were theorems of breathtaking elegance and power. A prime example is his celebrated representation theorem for distributive lattices. A distributive lattice is one where the meet and join operations interact in a way that mimics the interaction of and or in logic, or intersection and union in set theory. Birkhoff's theorem states a profound truth. Every finite distributive lattice is structurally identical to a lattice formed by a collection of sets, ordered by inclusion. This is a result of immense conceptual importance. It reveals that the abstract, axiomatically defined structure of a distributive lattice, for all its generality, is perfectly mirrored in the concrete intuitive world of sets and subsets. It provides a solid ground for our intuition, showing that these abstract systems are representations of something tangible. The creation of lattice theory provided a powerful new tool, a structural lens, through which to view a vast range of problems. Its influence has radiated outward from pure mathematics into remarkably diverse fields. In theoretical computer science, lattices provide the mathematical foundation for domain theory, which gives a rigorous semantics to programming languages, and they describe the type hierarchies in object-oriented programming. In logic, different logical systems correspond to different types of lattices. There is even a compelling, if still debated, research program that proposes a lattice of experimental propositions as the correct mathematical structure for the logic of quantum mechanics, a departure from the classical Boolean algebra of everyday experience. Through this initial monumental work, Garrett Birkhoff demonstrated a unique genius for seeing the universal in the particular, for constructing a grand, unified theory from a collection of whispers and hints. This achievement of building a coherent structure for order itself would become the intellectual springboard for an even more ambitious project, the search for the principles that govern algebraic structures of every conceivable kind. The intellectual momentum gained from structuring the very concept of order propelled Garrett Birkhoff toward a more expansive inquiry. His work on lattices provided a powerful concrete example of a new kind of algebraic system, one that stood alongside the classical structures of groups, rings, and fields that had dominated the 19th and early 20th centuries. In the mathematical environment of the 1930s, a curious pattern had become apparent to the keenest observers. A mathematician studying group theory would develop a proof for the isomorphism theorems. A colleague across the hall, working on ring theory, would independently formulate and prove a strikingly similar set of theorems. Then, a third would do the same for vector spaces. There is a certain economy of thought that mathematicians cherish, and the act of proving the same fundamental idea repeatedly in different guises begins to feel, to put it mildly, inefficient. It suggested a deeper unity, a common architectural grammar underlying these seemingly separate languages. The challenge was to articulate this grammar. This pursuit gave rise to the field we now call universal algebra. It was an audacious attempt to abstract away the particulars of any single structure, the specific axioms of a group, or the two distinct operations of a ring, and to study the properties of algebraic systems in their most general form. An algebra, in this new sweeping vision, was simply a set equipped with a collection of operations. The nature of these operations was secondary, their existence and their arity, meaning the number of inputs they take, were primary. This perspective allowed mathematicians to ask profound questions. What does it mean for one algebra to be a substructure of another? What constitutes a structure-preserving map, or homomorphism, between two entirely different types of algebras? How can we combine algebras to form new, more complex ones? These were the very concepts, subalgebra, homomorphism, direct product, that appeared again and again in the bespoke theories of groups and rings. Universal algebra sought to provide a single definitive account of them all. Within this ambitious program, Birkhoff furnished the cornerstone. His contribution, now known as the HSP theorem, or Birkhoff's variety theorem, stands as one of the most elegant and powerful results in modern algebra. It establishes a profound link between two different ways of looking at a class of algebras. One way is syntactic, through equations. A class of algebras defined by equations is called a variety. For example, the variety of all groups is defined by identities like the associative law, x times the quantity y times z equals the quantity x times y times z, and the existence of an identity element, and inverses. The variety of commutative rings adds the identity x times y equals y times x. These equations are the rules, the genetic code for a particular type of structure. The other way of looking at a class of algebras is semantic or operational. It involves observing what happens when you manipulate these algebras. Birkhoff identified three fundamental closure operations. The first is the taking of homomorphic images, which we can denote with H. A homomorphic image of an algebra is a simplified version of it, one that preserves all the operational relationships. Think of it as a low-resolution photograph that, while losing some detail, faithfully retains the overall structure and composition of the original scene. The second operation is the taking of subalgebras, denoted by S. This is the most intuitive process. A subalgebra is a smaller algebraic system living inside a larger one, using the same operations and being self-contained. The third is the formation of direct products, denoted by P. This operation allows one to build larger, more complicated algebras from simpler ones. Given two algebras, their direct product is a new algebra whose elements are ordered pairs, with operations performed component by component. It is a systematic way to construct composite systems. Birkhoff's theorem states, with breathtaking simplicity, that a class of algebras is a variety, that is, it can be defined by a set of equations if and only if it is closed under the operations of taking homomorphic images, subalgebras, and direct products. The class must contain all its own structural simplifications, all its own self-contained parts, and all the composite structures you can build from its members. This HSP theorem is a perfect bridge between syntax and semantics. It tells you that the algebraic way of describing a class through equations is completely equivalent to the structural closure-based way of describing it. If you have a collection of algebras that is robust under these three natural constructions, you are guaranteed that there exists a set of universal laws, a collection of identities that they all obey. Conversely, any set of laws defines a family of structures that is perfectly sealed under these same three constructions. The implications of this result radiate throughout mathematics and its applications. It provided a definitive toolkit for understanding what makes a class of algebraic structures natural and coherent. It gave a precise answer to the question of what kinds of properties can be defined by equations. For instance, the property of a group being finite, or a field having a specific number of elements, cannot be captured by equations alone, a fact made clear because the class of all finite groups is unclosed under the taking of direct products. The theorem became a foundational principle in model theory, the branch of logic that studies the relationship between formal theories and the mathematical structures that satisfy them. Furthermore, this highly abstract work found an unexpectedly fertile ground in the nascent field of theoretical computer science decades later. The formal specification of data types, for example, is essentially the task of defining a variety of algebras. The data type stack can be defined by equations governing the behavior of push and pop operations. Birkhoff's theorem guarantees that the models of this specification have a robust and predictable structure. The semantics of programming languages, the very meaning of computational processes, can be rigorously defined using algebraic structures, and universal algebra provides the framework for reasoning about these definitions. It supplies the deep theory that allows computer scientists to understand which properties of a system are preserved when it is simplified, combined with other systems, or when a part of it is isolated for analysis. The search for a unifying principle for the disparate branches of algebra yielded a tool of immense practical power, capable of taming the complexity of computational systems that were beyond imagination in the 1930s. This intellectual journey, from the specific structure of order in lattices to the universal principles governing all algebras, reveals a mind constantly seeking the most general, most powerful, and most elegant formulation. It was this same intellectual disposition, this capacity for profound abstraction, that would soon be called upon to face challenges of a completely different character, born from the crucible of global conflict. That very capacity for profound abstraction, honed on the ethereal structures of lattices and algebras, was indeed summoned to confront challenges of a starkly physical and violently pragmatic nature. The eruption of the Second World War reoriented the priorities of an entire generation of scientists, pulling them from the serene cloisters of academia into the urgent, high-stakes enterprise of military research. For Garrett Birkhoff, this transition represented a remarkable pivot, a moment where the search for universal principles in mathematics met the demand for specific, life-or-death answers in physics. He would emerge from this period as a central figure in the transformation of fluid dynamics from an empirically driven art into a rigorous mathematical science. His wartime work began at the Ballistic Research Laboratory at the Aberdeen Proving Ground in Maryland, a nexus of military science where the most pressing problems of ordnance were dissected. One of the most perplexing and potent of these was the phenomenon of the shaped charge. Military engineers knew that by lining a conical cavity in a block of explosive with a thin layer of metal, they could create a weapon of astonishing power. Upon detonation, the explosive pressure collapses the metal liner onto its central axis, forming a hypervelocity jet of metallic particles, almost a fluid, that could penetrate feet of solid steel armor. The effect was devastating, yet the underlying physics remained elusive, a piece of battlefield alchemy understood through trial and error. Birkhoff, alongside colleagues like John von Neumann, approached this violent, chaotic event with the cool lens of mathematical modeling. They proposed that the extreme pressures and temperatures involved allowed the metal jet to be treated as an incompressible, non-viscous or ideal fluid. This was a profound conceptual leap, applying the elegant mathematics of hydrodynamics to what was ostensibly a problem in solid mechanics and metallurgy. By modeling the collapsing liner and subsequent jet formation using the equations of potential flow, they could predict the jet's velocity, mass, and penetrating power with remarkable accuracy. This work led to the Birkhoff-Taylor theory of jet formation, a cornerstone in the design of anti-tank munitions. It was a clear demonstration of Birkhoff's core intellectual conviction that a well-chosen abstract model could distill the essence of a complex physical reality, providing predictive power where empirical methods offered only rough guidelines. This intense engagement with fluid dynamics exposed Birkhoff to the state of the entire field, and he found it wanting. Hydrodynamics, for all its practical importance in naval architecture, aeronautics, and ballistics, seemed to him a discipline rife with paradoxes and lacking a coherent theoretical foundation. He saw a collection of ad hoc models, brilliant experimental results, and beautiful but often misapplied partial differential equations. This intellectual dissatisfaction culminated in his 1950 book, Hydrodynamics, a study in logic, fact, and similitude. The title itself is a declaration of intent. This was a book with a purpose, a polemic aimed at cleaning the intellectual house of an entire scientific domain. Birkhoff's central argument was that many of the field's long-standing puzzles, such as D'Alembert's paradox, which famously predicts zero drag for a body moving through an ideal fluid, were artifacts of a failure to properly respect the role of symmetry and scaling. He championed the systematic use of dimensional analysis and group theory as the essential logical tools for constructing and validating fluid dynamics models. By considering the symmetry groups under which the laws of physics must remain invariant, such as translations, rotations, and changes in scale, one could deduce the necessary form of physical laws without resorting to endless experimentation. This was the mind of the universal algebraist at work, seeing the deep structural symmetries that govern physical phenomena. He argued that a model of a ship's wake, for instance, should be formally related to a smaller-scale model in a water tank through a precise group of scaling transformations. Any theoretical model that failed this test of similitude was, in his view, fundamentally flawed. The book was a call for rigor, an insistence that the language of modern algebra was essential for speaking sense about the flow of water and air. His theoretical contributions extended to specific fundamental problems within the field. Working with the Russian scientist N. Rott, he developed what is now known as the Birkhoff-Rott equation. This formidable non-linear integro-differential equation describes the evolution of a vortex sheet, the infinitesimally thin boundary layer that forms between two fluid layers moving at different speeds. This phenomenon, an instance of the Kelvin-Helmholtz instability, is ubiquitous, appearing in the curl of smoke from a cigarette, the patterns of clouds in the sky, and the turbulent wake behind a moving aircraft. The equation provided a powerful mathematical tool for analyzing the complex, chaotic behavior that arises from these simple interfaces, predicting how smooth sheets roll up into discrete vortices. The sheer complexity of the equations emerging from this work, both for shaped charges and for general fluid flow, pushed the limits of what could be solved with pen and paper. Here, Birkhoff's foresight proved decisive. He was among the first generation of mathematicians to grasp the transformative potential of the new electronic computers. At Aberdeen, he gained access to the ENIAC, one of the world's first general-purpose digital computers. He and his group became pioneers in using this room-sized behemoth of vacuum tubes and relays to perform numerical simulations of fluid dynamics problems. They were translating the abstract world of partial differential equations into the discrete arithmetic language of the machine. This work was the very genesis of a new field, computational fluid dynamics, or CFD. It established a new paradigm for scientific inquiry, a third way that complemented traditional theory and physical experimentation with digital simulation. The ability to model the flow of air over a wing or the explosive formation of a metallic jet inside a computer was born from this wartime necessity, guided by Birkhoff's unique synthesis of abstract mathematics and computational pragmatism. The intellectual journey through the crucible of war had equipped him with a new set of problems and a powerful new tool, setting the stage for his final, and perhaps most enduring, contributions to the mathematical sciences. The dawn of the atomic age presented a new and existentially potent class of problems demanding computational prowess. The immense power unlocked from the atom required an equally immense intellectual effort to control it. For Garrett Birkhoff, the experience of wartime computation with the Mark I computer was a prelude to a deeper engagement with the physics of the nuclear era. His attention turned toward the Westinghouse Bettis Atomic Power Laboratory, an institution grappling with one of the most complex engineering challenges of the 20th century, the design of safe and efficient nuclear reactors, particularly for the nascent nuclear submarine program. The core of a reactor, a maelstrom of neutron flux and heat transfer, was a system whose behavior was described by intricate elliptic partial differential equations. These equations, governing the steady-state distribution of neutrons, were mathematically elegant but analytically unsolvable for any realistic three-dimensional geometry. The challenge was profound. The engineers at Bettis could approximate these continuous equations by discretizing them, overlaying the reactor core with a conceptual grid, and writing down a vast system of linear algebraic equations, one for each point on the grid. A coarse grid might yield thousands of equations. A fine, accurate one could produce millions. The resulting computational task was staggering. Direct methods of solution, like the Gaussian elimination taught in introductory algebra courses, were completely infeasible. A computer attempting such a calculation would run for years, if it could even store the intermediate steps. The only viable path lay in iterative methods, algorithms that begin with a guess and progressively refine the solution in a series of steps, hopefully converging toward the true answer. Here Birkhoff located the precise intellectual void. The iterative methods in use, such as the successive over-relaxation or SOR method, often worked, but the reasons were obscure. Their convergence was a matter of empirical observation and hopeful guesswork, a dangerous proposition when dealing with reactor safety. The field required a rigorous mathematical foundation. It needed proofs of convergence, estimates of the rate of convergence, and a deep understanding of which methods were suitable for which classes of problems. Birkhoff, in collaboration with his brilliant student Richard Varga, provided precisely this foundation. They recognized that the question of convergence was fundamentally a problem in matrix theory. Each iterative step could be represented as a matrix multiplication. The convergence of the entire process depended on the properties of this iteration matrix, specifically its eigenvalues. Their work, culminating in the landmark 1962 monograph, Iterative Solution of Large Linear Systems, became the Bible for a generation of numerical analysts and engineers. Birkhoff and Varga established the rigorous connection between the spectral radius of the iteration matrix, that is, the largest absolute value of its eigenvalues, and the asymptotic rate of convergence of the method. They analyzed the specific structure of the matrices arising from the discretization of elliptic partial differential equations, proving theorems that guaranteed convergence for important classes of problems. This achievement married the abstract world of linear algebra and spectral theory with the urgent practical needs of nuclear engineering. It transformed the design of numerical algorithms from a craft into a science. The intellectual lineage is clear. The same mind that sought universal structures in algebra now sought the universal principles governing the convergence of numerical processes. His earlier work on ordered algebraic structures, like lattices, gave him a unique and powerful intuition for analyzing the monotonic convergence of these iterative schemes, viewing the sequence of approximate solutions as a progression within an ordered vector space. The intellectual trajectory of Garrett Birkhoff describes a grand unifying arc across the landscape of 20th century science. To view his career as a sequence of disparate interests, a foray into abstract algebra, a diversion into fluid dynamics, a final chapter in numerical analysis, is to miss the profound synthesis he achieved. His life's work offers a powerful counter-narrative to the perceived schism between pure and applied mathematics. For Birkhoff, the abstract and the concrete were inseparable partners in the quest for understanding. His journey reveals a singular coherent vision that the deepest and most powerful structures of mathematical thought are the essential keys to unlocking, modeling, and ultimately manipulating the physical world. His initial explorations of lattice theory and universal algebra were a search for the architectural bedrock of mathematics itself. He was looking for the common principles that govern seemingly different algebraic systems. This search for fundamental structure gave him a unique lens through which to view all subsequent problems. When he confronted the chaotic and beautiful complexity of fluid flow, he saw it as a domain crying out for rigorous mathematical description, a place where the abstract language of partial differential equations met physical reality. The war provided the catalyst, forcing the development of computational tools that could bridge the gap between the equations and their solutions. This led to his ultimate synthesis. In the humming relays of the Mark I and the silent pulsing cores of nuclear reactors, Birkhoff saw the future of scientific inquiry. He understood that the digital computer was more than a fast calculator. It was an experimental laboratory for exploring the consequences of mathematical models. His work on numerical methods for reactor physics was the capstone of this vision. It demonstrated conclusively that the most abstract concepts of matrix theory and functional analysis were the very tools required to ensure the stability and reliability of the most critical real-world computations. He established a paradigm that now dominates virtually every field of science and engineering, a powerful trinity of theoretical formulation, physical modeling, and high-performance computation. The legacy of Garrett Birkhoff, therefore, is a methodological one. It is the demonstration that abstraction is the most potent tool for practical application. His theorems in universal algebra echo in the logical foundations of computer science. His pioneering simulations of shape charges prefigured the entire field of computational fluid dynamics, a tool now indispensable for designing everything from airplanes to artificial hearts. His rigorous analysis of iterative methods
provides the mathematical guarantee for algorithms that run silently on supercomputers worldwide, forecasting weather, modeling financial markets, and simulating the birth of galaxies. Garrett Birkhoff's intellectual journey shows us that the path to understanding the tangible world of fluids, forces, and energy often begins in the ethereal realm of pure structure. He was a master architect of abstraction who used its blueprints to build a new and more powerful way of doing science.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.